All right, guys. So, yep. So what we're covering today is the property, what's called the property of equality for exponential equations. You're most likely, I'm going to refer to it as the 1-to-1 property. Because some books will refer to this as the 1-to-1 property. Some books will refer to this as the property of equality for exponential equations, or property of equality. Because when we talk about the property of equality, well, equality means what? Equal to. So we're talking about a property of equality for exponential equations. We're talking about them being equal in a way, shape, or form. If b is a positive real number other than 1, then b to the x is equal to b to the y if and only if x is equal to y. Because if the two bases are the same, the only thing that can really be different is the exponents. So if I can get both sides of the equation to have the same base, then whatever the exponents are have to be equal. So they gave us 3 to the x is equal to 3 to the 5th. Well, x has to be 5, because that's the only way that I can get 3 to the x to be the same as 3 to the 5th. The exponents have to be the same. So if we look at this first one here, now the notes are a little bit jumbled because I ran the copies off this morning, and after I got down there and looked at them, I realized that some of the notes, the homework questions, I think is on the front of page 2 or 3. So I somehow, in trying to print them off, pulled that one all the way down to where it is, and then cut the first property off. Because I always leave out the first page because it's homework questions, but because it got moved, it cut out the property. Different property. Okay. Now, when we look at any of these here, if I can get the two bases to be the same, then their exponents have to be the same also. So when we look at these two here, I've got 100 to the x is equal to 1/10 to the x minus 3. Now the two main numbers that I can see here are 110. Yes? Can I make 110 be the same, or 1/10 be the same? Well, yes. Because I can rewrite 100 as what? Because 100 is the same as 10 squared. Now the 1/10, I can actually move the 10 from the denominator to the numerator, but there's something I have to do to it. And what would that be? Huh? Because it would be a negative exponent. Because whenever we move a number from the numerator to the denominator, or denominator to the numerator, we move it above or below the fraction, the exponent changes from positive to negative, or negative to positive. It changes the sign of the exponent. And if a number, like here we had 10 in the denominator, doesn't have an exponent, well, it really does, we just don't write it, it is 1. If an exponent is not written, it is understood to be 1. So we can rewrite it as this here. So let's simplify it a little bit, because powers of powers multiply, so we can multiply those together. So 10 to the 2 to the x is the same as 10 to the is equal to 10. So I'm going to multiply x minus 3 by negative 1. Negative x plus 3, because it's affecting both the x and the negative 3. So I have an equation where both bases are the same. Bless you. Yes? So since the bases are the same, for these to be equal, the exponents must also be the same. So really we can say that 2x is equal to negative x plus 3. Any questions on how we got to this point here? Well, not yet. We still need to solve for the value of x. So what can we do in solving for the value of x? Huh? Well, we need all the variables on the same side, so we can, we'd add x to both sides. I always want to try to get the variables together first, numbers by themselves first, especially since the degree on any of the variables is 1. We don't have a quadratic or a higher degree polynomial. So we can do this here. Well, 2x plus x is equal to divide both sides by 3. X is equal to 1. It does do something. Any questions on any of this? Here. We good with this here so far? So let's look at this one here. So with these here, well, wait a minute. This one's a little bit easier than the one we just did because the bases are both the same. They're already the same. We don't have to do anything to get them to be the same. So it means our 3 minus 2x is equal to negative x. Because since the bases are the same, the exponents have to be also. That's the only way that these two can be equal. So what can we do first? Because we want to add 2x. We want to get the variables on the same side. Negative 2x plus 2x would be 0. Well, yeah, because these would be 0. Negative x plus 2x would be x, yes? No, you're good. You're good. And then we would have 3. So x is equal to 3. So we'll get there. Are there any questions on what we've done so far? Oh. Okay. So the bases are already the same, yes? Because I think some of you all are already looking at the fact that 2a is equal to negative a. We've already gotten to this point here, yes? So I need to get the values of a on the same side. So we can add a to both sides. Well, negative a plus a is 0. 2a plus a is 3a is equal to 0. A equals 0. Because there's two ways we can go about it. One of them is using a property, and one of them is using division. Because at this point, we can divide both sides by 3 and see that a is equal to 0. Actually, if I'm going to say it, why not? Divide by 3. 3a divided by 3 is just a. 0 divided by 3 is 0. Now, our zero product property that we use for factoring polynomials, any two things multiply together to equal 0, one of them has to be 0. Well, 3a equals 0. 3 times a is equal to 0. Well, 3 can't be 0, so a has to be 0. Because for really the zero product property, just stating any two things multiplied together that equal 0, one of them has to be 0. So it works even if one of them is a number. It's just really narrowing it down that a has to be the 0 value. So this here, a is equal to 0. Any questions on this here? Any questions over anything we've done thus far? So what can we do with this one here? Yes, because the bases are the same, we can go on and set it up as 2x plus 2 is equal to 3x. And then what? We would minus the 2x from both sides. 2x minus 2x is 0. 3x minus 2x would just be x is equal to, x is by itself, it's positive, and the only number in front of x is 1. So we've solved it. Any questions on any of these here? We like these here so far? Let's see here. Yep, okay. We do get in some other ones, and I really need to just rearrange this a little bit more. I'm going to approach this one a little bit differently, and it's not changing the process of what we're doing. It's just explaining the step of what we're doing a little bit better. Okay? Now, when we talked about logarithms, it's going to be 2 days ago, on Monday, we talked about if the base of the logarithm and what's inside are the same, they simplify out. Yes? So what I'm going to do for this one here is I'm going to apply log base 6 to both sides. So I'm going to take log base 6 of 6 to the negative 2a. And we'll have log base 6 of 6 to the 2 minus 3a. I'm applying log base 6 to both sides. And there's a reason I picked log base 6, and it'll be clear here in a second. To both sides of why we do this. Now, before we start simplifying and doing that there, our properties of powers, our logarithmic property of power, states if I have something inside the logarithm to an exponent, we can take that exponent and move it out front. Yes? So that means I can move this negative 2a and this whole 2 minus 3a, I can move both of them to the front of the logarithm. So I actually have negative 2a times log base 6 of 6 is equal to 2 minus 3a times log base 6 of 6. So any questions on anything we've done so far? So we used the power property that we learned on Monday to move those exponents out front, yes? Now the other property we had was, well, log base 6 of 6, this here is just 1. Log base 6 of 6, this here is just 1. So what we have left is that negative 2a is equal to 2 minus 3a. Well, wait a minute. Isn't that what our property of equality of exponential equations said? This is why it's true. Because if I can get both sides to be to the same base, really we can apply that logarithm with that base to both sides, which will simplify out, leaving us with just the exponents. This is why it works. This is why it works so nicely. Any questions on any of this here? Okay, well, what can we do next? We can add 3a to both sides. These here will cancel out. Well, negative 2a plus 3a is going to be a is equal to 2. So really those other steps, we don't necessarily need them, especially if the bases are the same. So if we look at this one here, I don't have one base on either side. I've got 2 and 1. Now they are all the same. They're all 6, yes? So could I combine the 6 to the 3m times 6 to the negative m? Yes. Because if the bases are the same, the exponents. Because 3m plus negative m would be 2m. Does anybody have a guess at what the value of m is going to be? It is going to be 0. Most likely, yes. So, since the bases are the same, it means that the exponents have to be the same also. At this point here, we can add 2m to both sides. And if we add 2m to both sides, we get that 4m is equal to 0, which means m has to be 0. Any questions over anything we've done so far? We good with all of this here? All right, we want to solve 3 to the 1 minus 2x is equal to 243. We need to make the bases the same. Now, if we can rewrite 243 as 3 to an exponent, that would be nice. So we want to see if we can rewrite 243 as 3 to a power. And we can just use a calculator to find this, because we can either do 243 divided by 3 and keep dividing by 3 until we hit 1. Or we can do it the other way and do 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81, 3 to the fifth will give us 243. We can keep increasing the power of 3 to see when we get to this point. But it does tell us that both bases are 3. We're able to get them so that both bases are the same. Which means for us that 1 minus 2x is equal to 5. Almost. Minus 1 from both sides. And we get that negative 2x is equal to, we can divide both sides by negative 2, which tells us x is equal to negative 2. Any questions on any of this here? Because exponents can be negatives, we just can't have, because exponents being negatives are fine. Because it's really just, it's a number in the numerator that should be in the denominator. So negative exponent is just moving it either from the denominator to the numerator or numerator to the denominator. It's just moving it across the fraction bar. Yep. Even roots, we cannot have negative numbers or negative roots. Okay. All right. So let's look at this one here. We have 4 to the negative 3x times 4 to the 3x. Or 4 to the negative 2x times 4 to the x. I don't know where I got 3x from. Is equal to 64. Okay. We need to get it as 4. I think that's where I was pulling the 3 from. And it would be negative x. Because negative 2x plus x would be negative x. 64 is 4 to the third. So, yeah, so we could say negative x is equal to 3. We can divide or multiply by negative 1, which will tell us x is equal to negative 3. Or we can kind of see, okay, well, negative x is equal to 3. So if I switch the sign on x from negative to positive, the other side has to switch also. So it becomes negative 3. We can almost think of the same way as if it was saying negative x equals negative 3. So x is equal to 3. We flip both signs. Any questions on this here before we look at the last, because this here I believe is the last exponential that we're going to look at before we start talking about logarithms. So there's two routes we can go with this here. And that is, and what I mean by that is I can rewrite 9 as 3 to a power, because 3 squared is 9. 81 I can rewrite as 3 to the 4th. So 3 to the 4th is 81. 3 squared is 9. So we can use that. Or we could actually use 9, because 9 squared is 81. Either one of them will give us the exact same answer. So we can rewrite 81 as 9 squared. Now 1/9 we would rewrite as 9 to the You're good? Yeah, we would rewrite 1/9 as 9 to the negative 1 because we want to move it from the denominator to the numerator. Any questions on this so far? So, powers of powers will multiply. So here we have 9 to the 2x is equal to 9 to the because the negative would affect not only the x, but the 3 as well. Now, since the bases are the same, we can set the exponents equal to each other. Which tells us 3x is equal to So with most of these exponentials and using this property of equality of exponential equations, I believe the only real way, especially if we can get the bases to be the same for these type here, the only way that these really get more difficult is if instead of 81 we had 27. So I'm not only having to fix one side, I'm also having to fix the other, because then I would need to get them into base 3. Is the only real way that this type gets harder. Now, the other type that we can have, and we will cover this tomorrow, is if the bases are not the same. If there's no way to rewrite it so that the bases are the same. So if we were talking about 4 to the 2x minus 3 is equal to 10, and I'll just leave it as this. Because I can rewrite 4 as 2 squared, but we cannot rewrite 10 as 2 to a power. So we'll have to go about it a little bit differently when I cannot rewrite both sides to the same base. We have to do it a little bit differently. Now the other property we're going to look at today is the property of equality of logarithmic equations. If b, x, and y are positive real numbers with b not equal to 1, then log base b of x is equal to log base b of y if and only if x is equal to y. Now, our other logarithmic property we covered on Monday was when we had a number to a logarithm, and the number that we have as the base and the base of the logarithm are the same. So it looked like b to the log base b. If we have this, then they simplified out. Log base b of x was just x because those logarithms simplified. So when we look at this here, the same property is true because you don't have to write this first step. Really what we're saying with this property of equality, since these bases are both the same, and even though they're not written, we know that the base for a natural log is what? E. Yeah, I don't know sign language for E. And this, there we go. So E, so if I put both sides, put them so that I have e to the natural log of 4x minus 7 and e to the natural log of x plus 5, well, e and the ln would simplify out, leaving us with just 4x minus 7 is equal to now we do need to be careful with logarithms, with natural logs and logarithms, because what's inside the logarithm cannot be negative. What is inside a logarithm cannot be negative. Yes, I would agree. I'd minus x from both sides. So we have 3x minus 7 is equal to. Then we can add 7 to both sides. Five. Divide both sides by 3, which tells me x is equal to and that is it here. So it's the same as what we were doing for exponentials. Now we can look back and make sure that we don't have any negatives inside the log. Because if I type it in, 4 times 4 is 16. 16 minus 7 is 9. So we have a positive number. 4 plus 5 is 9. We have a positive number, and they're actually both the same. So it works. Because we do not need a negative number inside the logarithms. Even if it's the same negative number, it does not work. We cannot have a negative inside of a log. If, when plugged in, it produces a negative number, then it is wrong. Because the reason I say that when it plugged in, because if we had, say, -1, and when I plugged it into both sides where the logarithms are, and I got 2 and 2, it's fine. But if it actually gave us a negative number, 7x minus 4 and 2x plus 11, if when x is plugged back in, those turn out to be negative, then it doesn't work. So just because x is negative doesn't guarantee it won't work. We have to plug it back in and check to make sure it does or does not work. Then it is not a solution. It is one of our extraneous solutions. A value that comes up as working for the function and how we solved it, but does not work in the original problem. Kind of like with geometry where we get negative length, but we have to throw those out because we don't measure in a negative length, we only measure in positive length. So it's kind of those situations. And if it works out that every x value gives us a negative inside the logarithm, then it is no solution. It works out that we actually didn't have a value that would make both sides be the same. Now, for the most part, we won't come across it too often with these here, but it is possible. Yes? Now for this one here, since we see that we have the natural log on both sides, we don't have to put it e to the ln of 7x minus 4 and e to the ln of 2x plus 11. We can just set them equal to each other. We don't have to do that process. I showed that to you to kind of see and prove that this property does work. So we can go on and solve. I would minus the 2x, yes. 7x minus 2x is 5x minus 4 is equal to then we would add 4 to both sides, which tells us 5x is equal to divide by 5, and x is equal to 3. And if we plugged it back into either one, it would work. Because 7 times 3 is 21, minus 4 is 17. 2 times 3 is 6, and 6 plus 11 is 17. You have two positive numbers, so it works. Any questions on any of this here so far? Do we need to see another example of one of these? Or do we feel comfortable with these? Because we can do this. I don't mind doing one of these. Mm-hmm. Yes. And let's go on and finish it up. I would go the other. I would minus the 2x. Now, is there anything wrong with minusing the 5x? Well, no. Because I'll go on and do that. Because I can minus the 5x. If you wrote the 2x, that's fine. Because if we minus 5x from both sides, we would get 0 is equal to, well, 2x minus 5x is negative 3x plus 9. So again, we still need to get the variable by itself. So from here, we can minus 9 from both sides, which will tell us that negative 9 is equal to negative divide both sides by negative 3, which tells us x is equal to 3. Now, if we'd have subtracted 2x from both sides, we would have got 3x is equal to 9. We can divide both sides by 3, which tells us x is equal to 3. So it doesn't matter which order we go. The reason that most often I will subtract the smaller of the numbers in front of the variable first, so 2x, is because it keeps us with a positive number in front of x. And I try to do a lot of these, if I can do it in less steps, I'll do it in less steps. Now, I will sometimes subtract the 5x first, even though it will give me negative 3x. But if I notice that that's going to lead to less steps in solving, I'll go that route. I try to avoid it if it's possible, but if it's not, I'll go on and do it. Any questions on this here? Do you feel comfortable with this here? Awesome. Yep. And that's it. So pretty much it's just understanding and seeing that if we have log or natural log on both sides, what's inside of them, we can set equal and solve. For our exponentials, as long as we get the bases to be the same, we can set what they are put to, their exponentials, equal to each other and solve. And that's it for all of this here.